Hi, my name is Chad Williams, and today we're going to talk about linear regression. So let's start off by making data. I'm going to do this in the same way that I did in my correlational video. We're going to create a matrix of 50 participants and two columns that are unfilled with numbers. We're going to add a first column to be a uniform distribution or uniform sample of 50 participants using any number between 0 and 10. Then that gives us this data. And what we're going to do is we're going to create a correlation with this. So we're going to take our second column and we're going to use our first column, and we're going to use a multiplication using an R norm function of 50 participants. So to match how many rows we have from the first column, a mean of 2, and a, let's say, standard deviation of let's say 1, just 1, not 0.1. So here what we're doing is we're using a normal distribution to sample numbers where the mean is going to be 2 and we have a standard deviation of 1. We're going to multiply these numbers by the first data, and that's going to give us a correlated second column. So if we do that like this, what we can do is then name our columns. So name our columns of our data as, let's just say, time 1 and time 2. So whatever happened between that maybe has an effect or not. Are they correlated? Does it not matter? And then just quickly, this is our data, time 1 and time 2. And we can plot that as a scatter plot like this. Cool. And so what we see is this correlational data, and I can create a linear regression. So LR results equals linear model, so LM. So what we want to do is we want to see if the information from time 1 gives us any information about time 2. So we're trying to predict time 2, so column 2 by column 1. Now what you see is we're using this tilde now, and that's talking about that we're predicting something. So time 1 is our x variable in this case, and time 2 is our y variable. We haven't used this kind of pattern before. What we'll see is in future videos, I'll add more to this here. So we can predict time 2 from possibly other factors more than just one factor. But here we're going to do a very simple linear regression. So let's see what we get from this. Our results gives us a y-intercept and a slope. So we can use that and we can plot that using the AB line function and our result variable. And that gives us a straight line through our data. But the question is this significant or not? We're going to use the Anova function with our results to find out. And what we see is our output here. So we have degrees of freedom, sums of squared, mean squared, F value, and our P value. So the first thing you might be looking at is the P value, and that's a very small number, so yeah, it's significant. Then we have our F value of 65.535. So our first degrees of freedom is K minus 1. So K is how many levels we have here, and we have two different times, time 1 and time 2. So K is 2 minus 1 is our degrees of freedom of 1. And our residual degrees of freedom is n minus k. So the number of people we have, so 50, minus how many levels we have, which is 2. So that equals 48. We can write this out as f is 1 comma 48. So degrees of freedom, the first one, and then the second one, equals 65.54. P is less than 0.0001. And there we go. There's the result of our linear regression. So yeah, there is a significant linear regression between these two variables.